Unraveling Time in a Distributed World, A Journey into Lamport Clocks. Chapter 1, Welcome to the Distributed Frontier, the Age of Decentralization. Imagine a world where everything you do, every piece of information you consume, and every transaction you make is handled by a single, monolithic supercomputer. A single point of failure, a single bottleneck. In such a world, a power outage, a hardware glitch, or an accidental unplugging could bring everything to a grinding halt. Thankfully, that's not the world we live in. We live in the age of decentralization, an era defined by distributed systems. What exactly is a distributed system? At its heart, it's a collection of independent computers, often called nodes or processes, that work together as a single, coherent system to achieve a common goal. Think of it like a highly coordinated orchestra, where each musician plays their part, but together they create music far richer than any solo performance. Or, consider a sophisticated ant colony, where individual ants perform simple tasks, yet the colony as a whole exhibits complex, intelligent behavior. These systems are no longer a niche topic for computer scientists. They are the invisible backbone of our modern world. When you unlock your smartphone and instantly access a weather forecast, stream a movie, or check your bank balance, you're interacting with a distributed system. Cloud computing, the engine behind countless online services, is one massive distributed system. Social media platforms, where your posts are instantly available to millions, rely on thousands of interconnected servers. Even modern vehicles are becoming distributed systems on wheels, with independent sensors and control units communicating over internal networks. The Internet of Things, with its myriad of smart devices, pushes the boundaries of distribution even further. Why did we embrace this distributed frontier? The reasons are compelling. Scalability. A single computer can only grow so large or handle so much traffic. By spreading the workload across many machines, a distributed system can handle immense amounts of data and requests, scaling up simply by adding more nodes. Reliability and fault tolerance. If one part of a distributed system fails, the others can often pick up the slack. This resilience is critical for services that must be always on, like emergency response systems or financial exchanges. It's the digital equivalent of don't put all your eggs in one basket. Performance. Work can be broken down and executed in parallel across multiple machines, leading to faster processing times and lower latency. Geographic distribution. Services can be placed physically closer to their users, reducing communication delays. This is how streaming services deliver content smoothly across continents. However, this increased power and flexibility come with a steep learning curve and a unique set of challenges. Coordinating these independent components is far from trivial. Imagine our ant colony, but now the ants occasionally go rogue, or their communication signals get garbled, or they simply disappear without a trace. The inherent complexities of distributed systems include concurrency, multiple events happening simultaneously or appearing to across different nodes. How do we ensure they don't step on each other's toes? No shared memory. Unlike a program running on a single computer that can access a common block of memory, nodes in a distributed system communicate only by sending messages over a network. This makes sharing information and maintaining a consistent view incredibly difficult. Network delays and unreliability. Messages can be lost, duplicated, or arrive out of order. Network links can be slow or temporarily fail. This unpredictable communication is a constant headache. Independent failures. A node can crash, freeze, or become isolated from the network at any moment, and other nodes must cope without it. Partial knowledge. No single node has a complete, up-to-the-minute view of the entire system's state. Each node operates based on its local information and messages it has received. At the core of many of these challenges lies a deceptively simple, yet profoundly complex concept. Time. How do you know what happened when there's no single, universally agreed-upon clock ticks across all participating machines? How do you ensure that two financial transactions, processed on different servers, are applied in the correct, causal order? How can you resolve a conflict if two users independently modify the same document at what appears to be the same time? Understanding and managing time in a distributed system isn't just an academic exercise. It's fundamental to building robust, coherent, and fault-tolerant applications. Without a clear mechanism to order events, chaos quickly ensues. This is where the genius of Leslie Lamport and his elegant solution, Lamport clocks, comes into play. They don't try to synchronize physical time. Instead, they offer a logical way to establish a crucial concept: causality. But before we reveal Lamport's brilliant insight, let's first fully appreciate the illusion of real time in this distributed frontier. Chapter 2. The illusion of global time. Why distributed systems suffer without order. In our everyday lives, time is a straightforward concept. A second is a second, a minute is a minute. We synchronize our watches, schedule meetings, and expect events to unfold predictably within this universal flow. We rely on time to tell us cause from effect. Event A happened at 10:00 a.m., then event B at 10:05 a.m., so a must have occurred before B. This intuitive understanding of synchronized, global time works perfectly in a centralized world, or when all processes are confined to a single machine. But once we step into the distributed frontier, this seemingly solid ground beneath our feet begins to crumble. The problem isn't that computers can't tell time. Every computer has a built-in clock, usually a crystal oscillator, that keeps track of the passing seconds. What's problematic is trying to get all these independent clocks to agree on the exact universal time. The challenges of physical clock synchronization. Clock drift. No two physical clocks run at precisely the same rate. Even highly accurate atomic clocks used in global positioning systems, GPS, exhibit minute variations. For standard computer clocks, these variations, known as clock drift, are significant. One computer's clock might run slightly faster, another slightly slower. Over hours or days, these tiny differences accumulate, leading to noticeable discrepancies. Imagine trying to coordinate a symphony, but each musician's metronome beats at a slightly different tempo. The result would be cacophony. Network Time Protocol, NTP, and its limitations. To combat drift, computers use protocols like NTP to synchronize their clocks with highly accurate time servers, e.g., those connected to atomic clocks. NTP works by exchanging time information, measuring network delays, and adjusting a computer's local clock to match. While NTP is incredibly effective and keeps our computers largely in sync, it's not perfect. Network latency. Messages take time to travel across networks. When a server sends its time to a client, that time is already slightly old by the time it arrives. While NTP tries to compensate for this, network unpredictability, variable delays, packet loss means perfect synchronization is impossible. Granularity. NTP can synchronize clocks to milliseconds or even microseconds, which sounds impressive. But in modern systems, events can happen within nanoseconds. For processes that communicate in rapid bursts, even microsecond differences can be critical. Trust and security. NTP relies on trusting external time sources. Malicious actors could theoretically provide incorrect time, disrupting distributed operations. The simultaneity paradox. What does it truly mean for two events on different machines to happen at the same time? If one machine's clock is lagging by a few milliseconds, an event recorded at 10:00.000 on that machine might actually be after an event recorded at 10:00.001 on a machine whose clock is running ahead. The timestamps alone can't reliably tell us which event actually occurred first in real time or if one caused the other. Why does ordering matter so much? The importance of causality. In distributed systems, the sequence of events is paramount. Consider a few scenarios. Financial transactions. Imagine Alice tries to transfer $100 from her bank account, which currently has $100, to Bob. At almost the same instant, she also tries to transfer $50 to Charlie from the same account. If these two transactions are processed on different bank servers, in what order should they be applied? If the $50 transfer is processed first, Alice correctly has $50 remaining for Bob. But if the $100 transfer is processed first, her account would briefly go to zero before the $50 transfer is attempted, likely leading to a rejection. The outcome depends entirely on the order. What if one server's clock says 10:01 and the other says 10:00? Relying purely on physical timestamps could lead to an inconsistent or incorrect final bank balance. Collaborative editing. Two people on different continents are simultaneously editing a shared document. Person A types, hello, at 10:00.00, UTC according to their computer. Person B types, world, at 10:00.002, UTC according to their computer. When their changes propagate, how do we combine them? What if A's computer clock was a fraction of a second ahead of B's? The physical timestamps could suggest hello came before world, but perhaps B actually typed their edit first, then reacted to B's change. The challenge is not just when, but what caused what. Distributed debugging. When a complex system malfunctions, developers need to understand the sequence of events that led to the error. If logs from different servers have slightly misaligned timestamps, it becomes incredibly difficult to reconstruct the true causal chain, hindering diagnosis and resolution. Did message X from server A cause the error on server B, or was server B already in a bad state when it received X? These examples highlight a critical distinction. What matters isn't necessarily the physical time an event occurred, but its causal relationship to other events. If event A directly influences or precedes event B, then we say a happened before B. This happened before relation, often denoted as a B, captures causality. If you send a message and I receive it, your sending clearly happened before my receiving. If I execute a command on my computer and then another, the first command happened before the second. The challenge is how to establish this causal order purely through messages exchanged between independent, unsynchronized clocks. This is precisely the profound problem that Leslie Lamport tackled. He realized that for many distributed system problems, we don't need clocks to perfectly tell physical time. We need them to tell us if one event could have causally influenced another. This breakthrough allowed him to define a logical sense of time that transcends the unpredictable nature of physical clocks, providing a bedrock for ordering events in a distributed world. The illusion of global physical time might plague distributed systems, but a new logical reality was about to emerge. Chapter 3. Lamport's Insight, Giving Events Their Rightful Place. In 1978, a paper titled Time, Clocks, and the Ordering of Events in a Distributed System by Leslie Lamport revolutionized how we think about time in computing. Before this, the prevailing assumption was that reliable distributed systems would somehow need perfectly synchronized physical clocks. Lamport's genius lay in dismissing this expensive and often impossible requirement. He realized that for many purposes, the actual physical time of an event was less important than its ordering relative to other events, especially when considering cause and effect. Lamport's key contribution was the introduction of a logical clock and the formal definition of the happen-before relation. He demonstrated how, even without perfectly synchronized physical clocks, systems could maintain a consistent view of event ordering, crucial for tasks like ensuring data consistency, debugging, and achieving agreement across multiple computers. The happen-before relation, right arrow, the foundation of causality. Lamport's happen-before relation is the bedrock upon which logical clocks are built. It defines a partial ordering of events that captures causality. Events within a single process. If A and B are events occurring on the same process, and A occurs before B, then a right arrow B. This is intuitive. Steps in a program execute sequentially. Message passing. If A is the event of sending a message by one process, and B is the event of receiving that message by another process, then a right arrow B, a message must be sent before it can be received. The send event causes the receive event. Transitivity. If a right arrow B and B right arrow C, then a right arrow C. This means if A caused B and B caused C, then a transitively caused C. Events that are not related by happen before are considered concurrent. This means there's no causal link between them, neither one directly influenced the other. The Lamport clock algorithm. Simple rules, profound impact. A Lamport clock is not a physical clock. It's just a single, non-decreasing integer counter maintained by each process. The power lies in the simple rules applied to update these counters. Rule 1. Internal event. When a process performs an internal event, e.g., executing a calculation, changing its state. It increments its local logical clock. Analogy: imagine you're writing notes in your personal diary. Every time you write something new, you increment a counter on that page, say from 5 to 6. This is your personal timeline. Rule 2. Sending a message. When a process sends a message, it first applies Rule 1, increments its local clock, and then attaches its current logical clock value to the message. Analogy: before you mail a letter, you write one more note in your diary, incrementing your counter, say from 6 to 7, and then you write sent with timestamp 7 on the letter itself. The message now carries your current logical time. Rule 3. Receiving a message. When a process receives a message, it updates its own local logical clock. It sets its clock to be the maximum of its current value and the timestamp carried by the incoming message. After this, it immediately applies Rule 1, increments its clock. Analogy: you receive a letter message that says sent with timestamp 7. Your current diary counter is, say, 4. You look at your counter 4 and the letter's timestamp, 7, choose the larger one, 7, and then you write a new note in your diary, incrementing that chosen number 7 to 8. So your diary counter jumps from 4 to 8. This ensures that your received note timestamp 8 is always logically after the sent note timestamp 7 from the sender. It effectively means you caught up to the sender's logical time and then moved forward. Visualizing Lamport clocks in action. A narrative example. Let's illustrate how these rules create a coherent ordering without physical clocks. Imagine 3 friends, Alice, Bob, and Carol, using a very simple messaging system. Each starts their personal Lamport clock at 0. Alice A starts at clock 0, Bob B starts at clock 0, Carol C starts at clock 0. Events unfold. Alice writes a thought in her diary. Alice's clock. 0 becomes 1, Rule 1. Bob writes a thought in his diary. Bob's clock. 0 becomes 1, Rule 1. Carol writes a thought in her diary. Carol's clock. 0 becomes 1, Rule 1. At this point, clocks are A, 1, B, 1, C, 1. Alice sends a message to Bob. First, Alice increments her clock, Rule 1, 1 becomes 2. Alice sends the message carrying timestamp 2. Alice's clock, 2. Bob receives Alice's message, timestamp 2. Bob compares his current clock, 1, with the message's timestamp, 2. He takes the maximum, max, 1, 2 equals 2. Then, Bob increments that value, Rule 1 for receiving. 2 becomes 3. Bob's clock, 3 current clocks, A2, B3, C1. Notice that Bob's clock jumped from 1 to 3, incorporating the knowledge of Alice's event. Bob sends a copy of that message, or a reply, to Carol. First, Bob increments his clock, Rule 1, 3 becomes 4. Bob sends the message carrying timestamp 4. Bob's clock, 4. Carol receives Bob's message, timestamp 4. Carol compares her current clock, 1, with the message's timestamp 4. She takes max, 1, 4 equals 4. Then, Carol increments that value, Rule 1 for receiving, 4 becomes 5. Carol's clock, 5 current clocks. A2, B4, C5. Alice sends another message, this time to Carol. First, Alice increments her clock, Rule 1, 2 becomes 3. Alice sends the message carrying timestamp 3. Alice's clock, 3. Carol receives Alice's message, timestamp 3. Carol compares her current clock, 5, with the message's timestamp 3. She takes max, 5, 3 equals 5. Then, Carol increments that value, Rule 1 for receiving, 5 becomes 6. Carol's clock, 6 final clock values for these example events. A3, B4, C6. What a Lamport timestamp means and what it doesn't. It reflects causality, the happen before guarantee. If event O in a distributed system causally happened, before event B, a right arrow B, then it is guaranteed that the Lamport timestamp of a C, A, will be strictly less than the Lamport timestamp of B, C, B. For example, Alice's send event, timestamp 2, truly happened before Bob's receive event, timestamp 3. This is the fundamental, most powerful guarantee. A later timestamp implies that event could have been causally influenced by events labeled with earlier timestamps. It does not reflect physical time. A higher Lamport timestamp does not mean an event occurred physically later. Look at Bob's clock being 4 while Alice's is 3. It doesn't mean Bob is chronologically ahead of Alice in real time. A process that's very active many internal events or receiving many messages, will have a rapidly increasing logical clock, even if physically little time has passed. Conversely, an inactive process's clock might increase slowly. The numbers are purely for logical ordering relative to other events. It does not imply causality if timestamps conflict. This is a crucial point regarding the partial order. If C, A, C, B, it does not necessarily mean that a right arrow B events can have numerically ordered Lamport timestamps, but still be concurrent, meaning neither causally influence the other. For instance, in our example, Alice's final internal event resulting in clock 3 and Bob's final internal event resulting in clock 4 are concurrent. Alice's event did not cause Bob's, and vice versa. There's no causal link here, even though C, Alice's final event, C, Bob's final event. The smaller timestamp merely indicates that Alice's local timeline for that event ended there, and Bob's was at a higher number due to other reasons. Lamport clocks elegantly untangle the complexities of event ordering in distributed systems. They replace the unreliable concept of a single, universal physical time with a dependable, causal ordering that is sufficient for many practical applications. They provide a simple yet powerful logical framework, allowing processes to agree on the sequence of causally related events, paving the way for more robust and consistent distributed applications. The next chapter will dive into exactly how these logical clocks find their purpose in the real world. Chapter 4, Beyond Theory, Practical Applications of Logical Clocks. Lamport clocks, with their elegant simplicity and powerful guarantees about causal ordering, might seem like an abstract theoretical construct. However, the principles they embody, primarily the ability to establish a consistent, happened-before relationship, are foundational to solving real-world challenges in distributed systems. While actual implementations might use slightly more advanced concepts, the core idea of logical time, championed by Lamport, remains indispensable. Let's explore some areas where Lamport's insight finds profound practical application, sometimes directly, sometimes as an underlying principle for more complex algorithms. 1. Distributed debugging and event tracing. Debugging a program running on a single machine is hard enough. Debugging a distributed system, where events unfold concurrently across many independent machines with no single point of observation, is a nightmare. This is where logical clocks shine. Imagine a complex transaction involving multiple services. A customer places an order, service A, inventory is checked, service B, payment is processed, service C, and a confirmation is sent, service A again. If something goes wrong, say, the order goes through but payment fails, how do you trace the precise sequence of events across these different services to pinpoint the failure? Each service can attach a Lamport timestamp to every significant event it logs, e.g., received order request, updated inventory, payment initiated, payment failed. When messages are exchanged between services, they carry these logical timestamps. If Service A sends a message to Service B's clock adjusts to ensure its processing of that message has a later Lamport timestamp. For instance, if Service A generates log entry order received T=10 and sends a message to Service B receives it, its clock becomes 11, and it generates log entry checking inventory for order T=11. Later, if Service C, after receiving a message from Service B, logs payment failed T=15, we know that the payment failure logically occurred after both the order reception and the inventory check, even if physically Service C's server itself might have a slow clock. Later, when collecting all the logs from all services, simply sorting them by their Lamport timestamps provides a causally consistent ordering of events. You can reconstruct the true story of the transaction, seeing exactly which event initiated another, regardless of what the physical clocks on the individual servers might have read. This ability to linearly replay a distributed execution based on causality is a critical tool for identifying bottlenecks, race conditions, and various failures. Without logical clocks, you'd be wrestling with log entries scattered across different servers, potentially out of physical time sync, making causal reasoning virtually impossible. 2. ensuring consistency in distributed databases and replicated data. One of the holy grails of distributed systems is consistency. If you write a piece of data to one server and then immediately try to read it from another server, which holds a replica of that data, you expect to see the updated value. However, due to network delays and concurrent writes, ensuring this can be incredibly challenging. Logical time offers a robust approach to conflict resolution and maintaining coherence. Consider a shared inventory system in an online store. Product X has 10 items. 2 customers try to buy product X. Customer A tries to buy 2, customer B tries to buy 5. These requests hit different replicas of the inventory database. Customer A's request arrives at replica 1. It sees 10 items, deducts 2, and records the new count as 8. It also assigns this update a Lamport timestamp, e.g., 50. Customer B's request arrives at replica 2. It also sees 10 items, because replica 2 hasn't received replica 1's update yet, deducts 5, and records the new count as 5. This update is assigned its own Lamport timestamp, e.g., 48. At this point, replica 1 thinks there are 8 items, replica 2 thinks there are 5. A conflict. When these updates propagate, how do we correctly merge them? Lamport clocks come to the rescue. One common strategy is last write wins based on logical timestamps. Since replica 1's update, timestamp 50, has a higher Lamport timestamp than replica 2's, timestamp 48. The system can decide that replica 1's update is the later event in the logical sense, and its value of 8 should prevail. This is a simple form of conflict resolution that uses logical clocks to establish a deterministic outcome even for concurrent operations. While more sophisticated systems might use vector clocks for stronger guarantees, the principle of using logical timestamps to order potentially conflicting updates is core. 3. Distributed mutual exclusion, Lamport's bakery algorithm. In traditional operating systems, mutual exclusion ensures that only one process can access a critical shared resource, like a database entry or a printer, at a time. In a distributed system, without shared memory or a central authority, this becomes complex. Leslie Lamport himself proposed a classical distributed mutual exclusion algorithm known as the bakery algorithm, inspired by a bakery where customers take numbers to be served in order. This algorithm uses Lamport clocks to ensure that processes agree on whose turn it is to enter the critical section, the part of code accessing the shared resource. Here's a simplified concept. Imagine several customers, processes, want to access the single counter, the critical section, at a busy bakery. Instead of waiting in a physical line, each customer takes a ticket number. This ticket number is derived from a Lamport timestamp. When a customer wants to enter, they assign themselves a Lamport timestamp and broadcast it to everyone else. Each customer then looks at all the ticket numbers other customers have taken. A customer is allowed to approach the counter only if their own ticket number, Lamport timestamp, is the smallest among all customers waiting. If 2 customers happen to get the same logical ticket number, which is possible for concurrent events, they can use their unique pre-assigned customer ID, process ID, as a tiebreaker. When a customer finishes at the counter, they announce they're done, allowing the next customer with the smallest ticket number to proceed. This algorithm beautifully demonstrates how Lamport clocks can provide a fair and consistent ordering mechanism for resource access across a distributed set of machines, preventing simultaneous access and ensuring orderly execution without any central coordinator. 4. Reliable message delivery and causal ordering in message queues. In systems that rely heavily on message passing, ensuring that messages are processed in their causal order is vital. If message B is sent because of message A, then it's crucial that message A is processed before message B, even if physical network conditions cause message B to arrive earlier. Imagine a user updating their profile picture, event A. Then, a separate service generates a thumbnail, event B, from that new picture. If event B's message somehow arrives at the processing queue before event A's message, perhaps due to network routing quirks, and the thumbnail generation starts before the new picture is fully uploaded, it could lead to errors. Message queues or streaming platforms can incorporate Lamport timestamps into their message headers. Consumers of these messages could then use these timestamps to reorder messages if necessary, guaranteeing that related events are processed in their correct causal sequence. This is particularly relevant for event-driven architectures, where the flow of logic is dictated by a stream of events. By prioritizing messages with lower Lamport timestamps, or by holding back messages until their causal predecessors have been processed, the system maintains a sane, predictable flow of data and operations. An illustrative anecdote: the online auction bid saga. Consider a scenario in a busy online auction system, where bids are handled by different servers to ensure speed and resilience. User Alex sees an item at $100 and decides to bid $105. This bid goes to server X processes it, records it as $105, and, following Lamport's rules, assigns it a logical timestamp of, say, 200. Almost simultaneously, user Bait on another computer also sees the price at $100 and bids $107. This bid goes to server Y. Server Y processes it, records it as $107, and assigns it a logical timestamp of, say, 198, because server Y was less busy and its clock values hadn't advanced as much yet. Now, both servers need to tell all the other auction servers and display clients about these bids. Imagine server YS update $107, T equals 198, reaches a display client first due to network routing. The client updates, current bid $107. Then server X's update, $105, T equals 200 arrives. If the client simply blindly takes the latest arriving update, it would show $105, a lower bid, which is illogical. But with Lamport clocks, the client compares the logical timestamps. Bid 1, $105, T equals 200. Bid 2, $107, T equals 198. Since Lamport clocks guarantee that if an event caused another, its timestamp will be lower, and since we know Bait's bid was not caused by Alex's, they conceptually viewed the same initial state, the system can make a crucial decision. It can recognize that while T equals 200 is numerically higher, the causal relationship isn't clear from the numbers alone in this concurrent case. Tools built on Lamport's ideas, like vector clocks, which we'll briefly touch on later, can even tell us if these events are truly concurrent. For simple, last right wins, for any event, using Lamport clocks would lead to the $105 winning because 198. This illustrates a limitation if strict causal order for all events is needed. However, where Lamport clocks excel is providing a simple metric that at least propagates causal dependencies correctly. For instance, if Alex's bid was seen by Bait before she made her counterbid, then Bait's counterbid would automatically receive a Lamport timestamp greater than Alex's. The crucial point is that Lamport timestamps provide a consistent numerical basis for interpreting chronological relationships that physical clocks cannot. They prevent the absurdity of an action appearing to occur before its cause or an earlier state overriding a later one based purely on unreliable physical clock differences. While Lamport clocks don't solve every coordination problem, their conceptual elegance and practical utility in establishing a causal ordering of events are indispensable. They provide a fundamental building block upon which more complex consistency and coordination strategies are constructed. However, like any tool, they have their limitations, which we will explore next. Chapter 5. The limits of logic, what Lamport clocks don't solve and what does. Lamport clocks are brilliant. They provide a simple, effective mechanism to establish a partial ordering of events in a distributed system, specifically guaranteeing that if event A causally happened before event B, then the Lamport timestamp of A will be strictly less than that of B. This is incredibly powerful for maintaining causality. However, it's crucial to understand what Lamport clocks don't do and how this opens the door for other, more complex solutions in the realm of distributed systems. The most significant limitation of Lamport clocks is that they only provide a partial order, not necessarily a total order. The ambiguity of concurrency and total order. Recall that if an event A happened before an event B, a right arrow B, then it's guaranteed that the Lamport clock value of A or C, A, will be less than the Lamport clock value of B, C, B. This is the fundamental property of Lamport clocks, but the converse is not true. If we observe that C, A, C, B, it does not necessarily mean that a right arrow B. Events with numerically ordered Lamport timestamps can still be concurrent. Let's revisit our three processes, P1, P2, P3 example. Suppose P1 performs an event E1 and its Lamport clock advances to C E1 equals 5. Separately, imagine P2 performs an event E2 and its Lamport clock advances to C E2 equals 6. Also, P3 performs an event E3 and its Lamport clock advances to C E3 equals 7. If these three events happen independently, without any messages being exchanged between P1, P2, and P3 regarding these specific events, then there is no causal relationship between them. Did E1 happen before E2? No. Did E2 happen before E1? No. Are E1 and E2 concurrent? Yes. They occurred independently without one influencing the other. Yet Lamport clocks assign them C, E1 equals 5 and C E2 equals 6. This means C E1, C E2, even though E1 did not cause E2. P2 merely happened to have a higher clock value at that instance, due to its own internal events or messages from other processes not relevant to P1. This is the core limitation. Lamport timestamps tell you if one event could have happened before another causally, but they don't tell you the reverse for concurrent events. They don't provide sufficient information to determine if two events are causally related or concurrent without further inspection of the system's execution history. Why is a total order often desired? While a partial order, knowing which events definitely influenced others, is sufficient for preserving causality and debugging, many distributed system problems require a total order of events. A total order means that for any two distinct events A and B in the system, it is always deterministically true that either A happened before B or B happened before A. There are no ties, no ambiguities, and no concurrent relationships in a total order. Everything has a definitive place in the sequence. Consider our online auction example again. While Lamport clocks helped sort the causally related bids, e.g., you can't bid higher than the current price before you see the current price. What if two users, Alice and Bob, both bid $10 concurrently on the same item, but neither saw the other's bid before making their own? Alice's bid on server A gets assigned Lamport timestamp C Elisabid equals 100. Bob's bid on server B gets assigned Lamport timestamp C Bobid equals 101. Who gets to be the first $10 bid? If the system simply uses the Lamport timestamp, it would say Alice's bid comes before Bob's because 101. But there's no inherent causal reason for that. It may be that server B was just slightly busier internally, causing its logical clock to advance faster. To truly resolve this and provide a single, deterministic outcome that all parties agree on, an arbitrary tiebreaker is often appended, such as the unique process ID, e.g., compare 100 server A ID with 101 server bid lexicographically. This creates an arbitrary total order, but not necessarily one based on true causality for these concurrent events. Total ordering is crucial for replicated state machines. Imagine a database being replicated across multiple servers. To ensure all servers remain identical, they must process the exact same sequence of operations. A total order of operations guarantees that all replicas apply changes in the same way, leading to identical states. Consensus. When multiple processes need to agree on a single value or decision, e.g., who is the leader, or which transaction gets committed, a mechanism to establish a globally agreed-upon order is vital. Global snapshots. Taking a consistent snapshot of a distributed system state often requires a logical cut that respects causality. While directly using Lamport clocks for this is complex, the underlying principles of ordering are paramount. Solutions for stronger ordering. To address the limitations of Lamport clocks and achieve stronger ordering guarantees, other concepts and algorithms have been developed. Vector clocks. Vector clocks take Lamport's concept of logical time a significant step further. Instead of a single integer, each process maintains a vector of logical clocks, where the vector has one entry for every process in the system. How they work: when process pi performs an internal event, it increments its own component in its vector, e.g., VCI++. When pi sends a message, it sends its full vector along with the message. When pj receives a message, it updates its vector by taking the element-wise maximum of its own vector, and the sender's vector, e.g., VCJK, equals max, VCJK, VC sender k, for all k. After this, pj increments its own component, VCJJ++. The power of vector clocks. Vector clocks provide a much richer, more accurate picture of causality. If VC, A, VC, B, meaning every component of VC, A is less than or equal to the corresponding component of VC, B, and at least one component is strictly less, then it is guaranteed that a right arrow B. Crucially, if neither VC, A is less than or equal to VC, B, nor vice versa, then O and B are concurrent. This means vector clocks can definitively tell you if two events were concurrent, something Lamport clocks cannot. Analogy: if a Lamport clock is like the sequence number on a single stream of consciousness, a vector clock is like tracking the sequence number for every person contributing to a massive, interconnected shared document. Each person has a counter, and when you receive an update, you not only advance your own counter but incorporate the knowledge of everyone else's counters up to that point. This gives you a precise version history of the entire system. Cost: the overhead is greater, as the size of the vector grows with the number of processes in the system. For systems with a very large and dynamic number of processes, this can become impractical. Consensus algorithms, e.g., Paxos, Raft. When the goal is to achieve a strict total order for operations or to ensure all processes agree on a sequence of events, then distributed consensus algorithms are employed. Algorithms like Paxos, developed by Lamport himself, and Raft are designed to make multiple processes agree on a single outcome. Even if some processes fail, messages are lost, or network partitions occur. They work by having processes propose values, vote, and elect leaders to ensure that all committed operations are performed in the same, globally agreed-upon sequence. They essentially create a distributed, fault-tolerant log of operations that all participants see in the identical order. These are much more complex than logical clocks, often involving multiple rounds of message exchanges, state machine replication, and intricate failure recovery mechanisms. They are the backbone of highly consistent distributed databases, distributed logs, and many blockchain technologies. Analogy: if logical clocks ensure that everyone knows their own contributions and whose work came before theirs, consensus algorithms are like an elaborate, highly formalized parliamentary procedure that debates and votes on every action to ensure everyone agrees on the final, rigid, non-negotiable order of what happened. There's no ambiguity. Once something is agreed upon, it's set in stone for everyone. Distributed transactions and two-phase commit. When an operation involves updating data across multiple independent databases, maintaining transactional integrity, atomicity, consistency, isolation, durability, acid properties, across these separate systems is a significant challenge. Algorithms like two-phase commit, 2PC, are used to ensure that either all parts of a distributed transaction commit successfully, all systems make their changes permanent, or all are rolled back, none make their changes permanent. While not directly using Lamport clocks, they are another mechanism to achieve agreement and order across disparate systems, often relying on a coordinator process and strict messaging protocols to ensure that all participants arrive at the same outcome for a given transaction. The enduring relevance of Lamport clocks. Despite their limitations when it comes to total ordering or detecting precise concurrency, Lamport clocks are far from obsolete. They provide the simplest and most efficient way to capture the fundamental happen-before relationship. This is often all that is needed for certain debugging scenarios, log analysis, or optimistic replication strategies where eventual consistency is acceptable. They serve as the conceptual stepping stone to understanding more complex logical time systems like vector clocks. Indeed, vector clocks are a direct extension of Lamport's original ideas. The principles they introduced, logical time, causality, underpin virtually all advanced distributed system designs. Even consensus algorithms, while not explicitly using Lamport clocks in their operation, rely on the deep understanding of event ordering and causality that Lamport elucidated. In essence, Lamport clocks offer a lightweight, foundational layer for understanding and ordering events. When stronger guarantees are required, especially a strict, universally agreed-upon total order or precise concurrency detection, the system builder must graduate to more complex algorithms. But the journey of understanding distributed systems always begins with Lamport's elegant separation of physical time from causal event ordering. Knowing what they can't do helps us appreciate where to apply other, more specialized tools. Chapter 6, Real-World Rhapsody, Case Studies and Success Stories. It's one thing to understand the theoretical elegance of Lamport clocks and the happen-before relation. It's another to see how these abstract concepts translate into the robust, reliable, and seemingly seamless digital experiences we take for granted every day. While you won't typically find Lamport clock explicitly mentioned in the marketing materials for your favorite app, the principles they introduced are woven into the fabric of many distributed systems. They are the quiet, unsung heroes, ensuring consistency and preventing chaos behind the scenes. Let's look at a few simplified case studies where the need for, or the application of, logical ordering is paramount. Case Study 1. Collaborative document editing, e.g., Google Docs simplified. Imagine you and a colleague, Jane, are collaborating on a single document, perhaps a project proposal. You're in New York, Jane is in London. You both have the document open, making changes simultaneously. You New York, type the quick brown fox. Your computer timestamps this local edit with your current Lamport clock value, say L equals 100. Jane, London. Simultaneously, Jane types jumps over the lazy dog. Her computer timestamps this local edit with her current Lamport clock value, say L equals 98. Her machine's internal clock happened to be slightly behind yours, or yours had more internal activity. Both of your edits are then sent to a central server that reconciles changes. In a world without logical ordering, the server might simply receive Jane's update first due to network latency, then your update later. If it only considers physical arrival time, it might mistakenly apply your later edit L equals 100 on top of Jane's L equals 98, potentially overwriting Jane's text or creating a confusing mismatch. However, using the principles of logical clocks and more advanced techniques like vector clocks, which build on them, the system understands causality. Each edit is stamped with a logical clock value, like 100 for your edit and 98 for Jane's. When the server receives these edits, it doesn't just look at physical arrival time. It examines the logical timestamps. Even if Jane's edit, L equals 98, arrives first physically, the system can determine that it's a concurrent edit relative to yours because neither caused the other, based on a deeper analysis of the logical timestamps. E.g., neither edit's timestamp fully dominates the other as it would in a causal chain. More sophisticated systems use these logical timestamps to merge the changes intelligently. They might keep both changes or use operational transformation to ensure both, the quick brown fox and jumps over the lazy dog, are correctly inserted without clobbering each other, ensuring that the final document reflects both contributions correctly and consistently for all users. The impact: without logical ordering, collaborative editing would be a nightmare of lost changes, overwritten content, and an inability to reconcile simultaneous contributions. It would be impossible to deterministically reconstruct the sequence of edits in a way that respects the user's intentions. Logical clocks ensure that even when concurrent events happen, the system has a consistent way to handle them, leading to a smooth and reliable user experience. Case Study 2. Distributed key-value stores and cloud storage, e.g., simplified Amazon S3 Apache Cassandra. Many modern cloud storage services and distributed databases don't aim for immediate, strong consistency everywhere, where everyone sees the absolute latest data instantly. Instead, they often focus on eventual consistency, supplemented with conflict resolution. This means that if you update data, it might take a moment for that update to propagate to all copies, but eventually, all copies will converge to the same state. Logical clocks play a crucial role in deciding what same state means when conflicts occur. Consider a simple cloud storage service where you can upload and overwrite files. The file myphoto.jpg is replicated across 3 servers, server A, server B, server C for reliability. Scenario 1, simple update. You upload myphoto of 1.jpg to server A. Server A assigns it a logical timestamp, e.g., L equals 50. Server A then propagates this update with L equals 50 to server B and see all copies converge to myphoto of 1.jpg with L equals 50. Scenario 2, concurrent updates and conflict resolution. You upload myphoto of 2.jpg to server A assigns it L equals 100. Almost simultaneously, your friend uploads myphoto of 3.jpg, a different version, to server B assigns it L equals 98. Both server A and server B then try to propagate their updates to server C. Whose photo wins? If we just look at the photo content, there's a conflict. This is where logical timestamps become the tiebreaker. The system can implement a conflict resolution policy like last write wins, where last is defined by the highest logical timestamp. In this case, myphoto of 2.jpg, L equals 100, would win over myphoto of 3.jpg, L equals 98. Server C and all other replicas would eventually converge on myphoto v2.jpg as the canonical version. The impact? This approach allows for high availability and performance even under heavy load and network issues. The system doesn't have to wait for all replicas to acknowledge an update before proceeding. Instead, it relies on logical clocks to resolve conflicts deterministically when they eventually meet. This provides a clear, consistent mechanism for converging on a single data state, preventing data corruption and ensuring users eventually see the right version of their data. Case Study 3. Ensuring correct message display in chat applications. Think about any modern messaging app. You participate in a group chat, and messages appear in a clear, linear sequence. But behind the scenes, messages from different users, on different devices, travel through a network to a central message broker and then back out to participants. What ensures that replies appear after the original message, even if network delays cause them to arrive out of order? User Alice sends message 1, anyone keen for lunch? Processed by server X gets Lamport timestamp L equals 50. User Bob sees message 1 on his device and replies message 2. Yes, I am. Processed by server Y gets Lamport timestamp L equals 55. User Carol sees message 2 on her device and replies message 3. Me too. Where? Processed by server Z gets Lamport timestamp L equals 60. Now, imagine due to network congestion, Carol's message 3, L equals 60, arrives at your device before Bob's message 2, L equals 55. If your app simply displayed messages in the order they physically arrived, your chat history would look nonsensical. Carol's message 3, me too, where? Alice's message 1, anyone keen for lunch? Bob's message 2, yes, I am. This is obviously broken. This is where the causal ordering provided by logical clocks saves the day. Each message implicitly or explicitly, in headers, carries a logical timestamp. When your chat app receives messages, it doesn't display them immediately. Instead, it uses these logical timestamps to buffer and reorder them. Your app receives Carol's message 3, L equals 60. It checks its logical timestamp. Your app receives Alice's message 1, L equals 50. Oh, this is lower than the previous one. It displays message 1. Your app receives Bob's message 2, L equals 55. It sees this is higher than message 1, but lower than message 3, and ensures message 2 is displayed after message 1, but before message 3. The impact. This simple yet powerful mechanism ensures that all participants in a chat thread see the conversation unfold in the correct causal order, not just the order their network happened to deliver messages. It maintains the conversational flow and makes distributed communication understandable, even across vast geographic distances and unreliable networks. These examples illustrate that Lamport clocks, while simple, are not merely academic curiosities. They represent a fundamental breakthrough in understanding and managing time in computer systems. By disentangling the complex notion of physical time from the crucial concept of causality, Lamport provided the theoretical underpinning for a multitude of distributed algorithms and systems that power our modern world. They demonstrate that sometimes, a logical, abstract system can be far more reliable and useful than a direct attempt to mimic physical reality. The principles Lamport pioneered continue to evolve and inspire new research. As distributed systems grow ever more complex and ubiquitous, the lessons from Lamport's work become even more critical for building the next generation of resilient and scalable applications. But where do we go from here? What challenges remain, and how might logical time concepts continue to shape the future of coordination? That's what we'll explore in our final chapter. Chapter 7. The Future of Coordination. Where do we go from here? Our journey through the distributed frontier began with an appreciation for the vast, interconnected systems that power our modern world. We saw how the promise of scalability, reliability, and performance lured us away from monolithic designs, but also introduced a spectrum of profound challenges. Chief among these was the illusion of global, synchronized time, a concept so ingrained in our everyday lives, yet utterly unreliable and even misleading in a decentralized environment. Clock drift, network latency, and the fundamental complexities of physical synchronization rendered traditional timestamps insufficient for truly understanding the causality of events across independent machines. Then came Lamport's groundbreaking insight. He didn't try to fix physical clocks, he cleverly sidestepped the problem altogether. By introducing a simple yet powerful set of rules for maintaining logical clocks and defining the happen-before relation, Leslie Lamport provided a robust mechanism for establishing the causal order of events. This elegant solution allows processes to agree on what happened after what, which is often far more important than when it happened, according to an imprecise physical timepiece. We saw how this principle underpins practical applications from distributed debugging that reconstructs error sequences, to ensuring consistency in databases, and even to orchestrating resource access in complex systems. However, as we explored, Lamport clocks, while foundational, are not a panacea. Their primary limitation lies in providing only a partial order, meaning concurrent events, those without a causal link, can have arbitrary logical timestamps relative to each other. This led us to explore more sophisticated concepts like vector clocks, which offer richer insights into concurrency, and powerful consensus algorithms, like Paxos and Raft, which create a strict total order of events, guaranteeing absolute agreement even in the face of failures. So, where does this leave us? And where do we go from here in the ever-evolving landscape of distributed systems? The enduring legacy of logical time. The direct application of Lamport clocks might be less common in highly specialized modern systems that choose more complex consensus mechanisms. Yet, Lamport's true enduring legacy is not just the algorithm itself, but the profound mindset it introduced. Decoupling from physical time. The realization that many synchronization problems don't need absolute physical time, but rather a reliable understanding of causality. The happen-before paradigm. This fundamental concept of ordering, regardless of implementation, is now integral to designing any distributed system that values consistency and predictability. Every time a distributed database resolves a conflict or a messaging system ensures messages are processed in a sensible sequence, the ghost of happened before is at work. A stepping stone. Lamport's work serves as the most accessible entry point into the complex world of distributed system theory. Understanding it unlocks the door to comprehending vector clocks, hybrid logical clocks, conflict-free replicated data types, CRDTS, and the nuances of various consistency models, challenges, and research directions in a hyper-distributed world. The distributed frontier is only expanding. The challenges of coordination, consistency, and time are becoming even more acute with new architectural patterns and computational paradigms. Extreme scale and heterogeneity. We're moving toward systems with billions of devices, from tiny IoT sensors to massive cloud data centers. Ensuring consistent global state and timely event processing across such vast, diverse, and often unreliable networks stretches current coordination mechanisms to their limits. Edge computing and serverless. Computation is moving closer to data sources, edge computing, and becoming increasingly ephemeral, serverless functions. How do we maintain causal ordering and strong consistency when processing components are transient, geographically dispersed, and communicate over potentially unstable links? New forms of lightweight logical clocks and synchronization might be needed. Blockchain and decentralized trust. Technologies like blockchain use sophisticated consensus mechanisms to establish a globally agreed-upon, immutable order of transactions without any central authority. They are, in essence, distributed ledgers that meticulously apply the principles of ensuring a consistent, single timeline for events, often relying on cryptographic proofs in addition to logical ordering. This area continues to push the boundaries of fault tolerance and trust in truly decentralized environments. Determinism and debugging at scale. As systems grow, debugging becomes incredibly difficult. The ability to deterministically replay executions using strong causal ordering, like that provided by sophisticated logical clocks or event sourcing, remains a critical area of research for building more robust and understandable ultra-large systems. Beyond timestamps, causality in data science and AI, understanding causality isn't just for system engineers anymore. In complex data pipelines and AI systems, discerning which events truly influenced an outcome is crucial for interpretability, debugging, and fairness. The principles of logical ordering, originally applied to system events, are now being adapted to understand relationships within vast datasets. A continuing adventure. The initial challenges that drove Leslie Lamport to formalize his concept of logical time are not just still relevant, they are evolving and multiplying. The need for robust coordination, for discerning cause from effect, and for building coherent systems out of inherently chaotic components remains a fundamental mission. The genius of Lamport clocks lies in their elegant simplicity and their power to establish a concept previously thought impossible. A reliable, logical understanding of time across a fragmented landscape. It is a testament to the power of abstract thought, demonstrating that sometimes the most profound solutions emerge not from building more complex machinery, but from fundamentally rethinking our assumptions about reality. As you navigate the ever-growing complexities of the digital age, remember the unassuming power of the Lamport clock. It reminds us that in a distributed world, it's not always about having the right time, but about knowing the right order. And that simple, profound distinction continues to shape the reliable, resilient, and engaging systems that define our future.